a neural model of ultra-fast learning using natural language instructions. In typical laboratory experiments, non-linguistic animals such as rats typically take weeks to learn a task, whereas humans exhibit strong initial performance on previously unseen tasks, giving linguistic instructions and a few training examples. We want to know what accounts for this rapid adaptation of performance for instructed tasks in humans, and if we can build a model that exhibits this fast adaptability based on linguistic inputs. We succeed in building such a model, but only with a language processing scheme that is sensitive to sentence level semantics. We establish this by testing two main types of models, a one-hot vector model and instructed models. Each model consists of a multitasking RNN that attempts to perform many cognitive tasks simultaneously. Models differ in how task type information is represented. One-hot vector models receive a one-hot encoding of the current task type, whereas in instructed models, a language module is used to embed natural language instructions into a low-dimensional vector that gets passed to the RNN. For language modules, we use two different types of pre-trained transformers. One, GPT-2, is trained on a massive corpus of text to predict next word. The second, SBERT, is trained on a similar word prediction objective, but importantly receives additional supervised pre-training on sentence level semantics. In this task, the network receives two input sentences and is asked to categorize the relationship between those sentences. To fine-tune the weights of these modules to our task instructions, we either let the gradient flow end-to-end from the errors in the motor output, or separately train on categorizing the task type based on instruction input. In each of our 16 tasks, we receive a fixation cue, inputs from two sensory modalities, and task type information as input. The model then attempts to respond in the proper direction given these inputs and the task type. Models are trained with mean squared error loss on target responses, and trials are interleaved to allow the network to perform all tasks simultaneously. To test the ability of instructed models to quickly learn unseen tasks, we train on a training set of 15 tasks until asymptotic performance, and then assess learning on 100 example trials of the 16th held at task. We find that the SBERT trained end-to-end is our best performing model, shown by the purple curve here. Averaged across all holdout tasks, SBERT end-to-end achieves near 80% zero-shot performance, whereas our non-linguistic model only achieves around 30%. Learning curves for 4 example tasks are shown on the right. Across all tasks, SBERT end-to-end, shown by the purple curve, is our top performing model. Importantly, GPT-2 fails to induce fast learning beyond that exhibited by our one-hot model, suggesting that sentence level knowledge is a crucial aspect of SBERT success. To examine how SBERT end-to-end can support such strong performance for unseen tasks, we do PCA of RNN hidden activity directly prior to stimulus onset, as well as for instruction embeddings produced by the language module. This analysis was done for 250 trials for each of the 4 kinds of decision-making tasks, but on networks where anti-decision-making was held out of training. This means neither network had ever seen an anti-decision-making trial before. What we would expect to find is that anti-decision-making activity resides in the same region of space as anti-multisensory decision-making, which shares many of the same task demands. For our SBERT model, we find this to be true. However, in our non-linguistic one-hot model, activity for the held-out anti-DM task resides closer to multi-DM and decision-making, which do not share the relevant task demands. Further, though the language module has likewise seen no examples of anti-decision-making instructions before, it was nonetheless able to infer a structure on embeddings isomorphic to the one shown in the RNN hidden activity. This is wholly based on the semantic relationship between previously encountered instructions. Instructed models with SBERT trained end-to-end display fast adaptability to novel tasks, showing near 80% zero-shot performance on average. This fast adaptability is supported by the RNN's ability to immediately cue proper hidden activity in a region of space according to the task demands. We hope that this model can lay the groundwork for future theory-guided investigations of language-modulated task representations in the brain.